Artificial intelligence is moving from simple generation to complex reasoning tasks that rely on continuous planning and reinforcement learning loops. Historically, a one-size-fits-all accelerator handled every task, but the specialized requirements of training and serving have begun to pull in opposite directions. Pre-training massive frontier models demands pure data throughput, while executing real-time agentic reasoning is strictly bound by low-latency constraints. To sustain these divergent workloads, Google has split its hardware architecture at the silicon level. Designing machine learning hardware requires balancing two opposing forces, maximizing model flops utilization for high-speed training and overcoming the memory wall to serve fast inference. This chart plots historical AI workloads. The infrastructure needs for training and inference used to be clustered tightly near the center. But mapping trillion-parameter pre-training against the demands of real-time agentic inference empties the center out. To address these extreme outer boundaries, Google built two distinct 8th-generation TPUs, the throughput-optimized TPU 8T and the latency-optimized TPU 8I. Explicitly dividing the hardware into specialized pre-training and serving engines is the only viable path to maintain computational efficiency at trillion-parameter scale. At megascale, the primary friction point isn't always compute power. Clusters frequently stall waiting for data ingestion and vector operations, leaving the arithmetic cores completely idle. This block diagram shows the architecture of the TPU 8T matrix multiply unit. By moving block-scale multiplication directly inside the MXU boundary, the chip reduces overhead wait times. The hardware natively supports lower precision FP4 quantization inside the MXU, unburdening the primary tensor cores. This specific structural balance minimizes the time the chip is exposed to vector operations, enabling finer-grained offloads to secondary threads. Shifting block-scale math and quantization directly into the MXU allows engineers to push the absolute limits of model flops utilization across the entire compute stack. Optimizing a single processor solves only part of the equation when models require scaling well past a single 9,600-chip superpod. This cluster map tracks the scale-out architecture. With JAX and the Virgo networking fabric, a single superpod forms a non-blocking array of over 1 million chips. The system integrates direct-to-chip RDMA access, pushing 10 terabytes per second of throughput straight to the hardware. Bypassing standard CPU nodes entirely removes the storage bandwidth choke points that historically crippled distributed training at megascale. On the opposite end of the spectrum is the TPU 8i, engineered to overcome the latency wall. Complex chain-of-thought reasoning relies on autoregressive decoding, a process constrained entirely by physical time. This timeline visualizes those decoding operations. You can see a substantial block of time where cores sit completely idle, waiting for long context memory retrieval. Traditionally, accelerators relied on off-chip high-bandwidth memory, or HBM, to store this context. The physical transit time required to fetch data from HBM is what causes those idle delays. The TPU 8i solves this by tripling the amount of on-chip SRAM, hosting the entire key-value cache locally, and cutting off the HBM detour entirely. By keeping the KV cache strictly on the silicon, the architecture drastically reduces core wait times, making it physically possible to serve massive context windows in real time. Real-time inference also introduces a distinct networking challenge. Mixture of experts models require dense, cross-chip, all-to-all collective communications to function. This network visualization models a traditional 3D torus mesh. When executing these cross-chip lookups, a single data packet has to make multiple sequential switch hops to reach its destination. Across a massive cluster, those numerous physical hops compound, creating severe tail latency. The TPU 8i abandons the torus for a hierarchical board-fly topology, physically compacting the network diameter to require fewer total hops, shortening the physical network diameter and routing data through a specialized collectives acceleration engine cuts communication latency by up to 50%. Shrinking the distance data has to travel is the absolute prerequisite for enabling the massive concurrent agent throughput demanded by real-time reinforcement learning loops. Engineering circuit logic at this density eventually exhausted the limits of manual human optimization. Google deployed AlphaEvolve, a reinforcement learning coding agent tasked specifically with optimizing the lowest levels of hardware stacks. Tasked with improving matrix multiplication, the agent discovered a mathematically counterintuitive, highly efficient circuit design that humans had not found in over 50 years. That AI-generated logic routing was adopted and printed directly into the physical silicon of these 8th-generation TPUs. This creates a recursive loop where software agents actively dictate the physical routing of their own next-generation hardware bodies. The TPU V8 is the direct continuation of Google DeepMind's decade-long strategy, utilizing specialized hardware to crack intractable problems. We saw this baseline established when AlphaGo mastered complex multi-step games on early TPU iterations. The scale then escalated to biology, using AlphaFold to predict the three-dimensional structures of nearly all known proteins. That computational achievement yielded a discovery recognized by the Nobel Prize. This diagram outlines the resulting dual-engine infrastructure, the TPU-8T driving massive-scale pre-training, seamlessly feeding into the low-latency agentic serving of the TPU-8I. This bifurcated full-stack architecture provides the essential bedrock for autonomous scientific discovery and systems that think and act alongside us as partners in discovery.